Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we are going to introduce confidence intervals for proportions. Okay, so let's begin. Before we start talking about confidence intervals for proportions, let me remind you about what we have already learned together, right? So we have already constructed confidence intervals for a mean, right? And the assumption was that our sample came from a normal distribution, right? With the variance sigma squared known, right? And that the mean mu was unknown. That's why we wanted a confidence interval for mu. So in practice, the mean and the variance both are going to be unknown. So in practice, one way of applying that result without making that assumption that sigma, the standard deviation, is known would be this. If you have a big sample size, then, well, in that case you could assume that sigma is basically known. You could estimate it and think that it's close enough to being the actual sigma, right? The assumption of independence and of these guys being identically distributed, that's important, right? And that we have a random sample. Okay, anyway, but you have seen and you have applied that formula before. Point estimate plus minus margin of error, where this guy, the critical value, C of alpha divided by 2, is a number from a normal 0, 1, such that the area to its right is alpha divided by 2, if you have the positive version. If you have minus C of alpha divided by 2, that means that the area to the left is alpha divided by 2. Okay? Anyway, now let's try and see how we could use this to come up with a formula for the confidence interval for a proportion P. So confidence interval for proportion P. So let's consider the following 0, 1 variable. Let yi be 1 if the ith observation from your sample is a success. And we know that that is relative. It depends on what you are interested in. And then it's going to be 0 otherwise. Okay? Otherwise. So this guy, this 0, 1 variable, is helping you to keep track of your successes, right? And you're going to have 0 if you have a failure. Okay? So now P represents the probability that your random variable is 1, or in other words, this guy is the probability of success, right? P represents the probability of success, and that implies as well that the complement would be the probability of failure. Make sense? Okay. So now something more. The expected value, or mean, for that random variable yi, we can easily show that it is P. And the variance we can also easily show that it's p times 1 minus p. Give it a shot. Okay, it isn't that complicated. Just use the definition of expected value and variance for that variable yi. Okay, now let's think about what we know, right? Y bar, and I'm mentioning this guy because, you know, we have that in our formula for the confidence interval. We know that y bar is the sum of the yi's divided by n, the sample size. Okay, but another way of thinking about it would be this: the number of successes in our sample divided by n, right? Because if you have the sum of these yi's, it's going to be 0 if you have failures. So it's only keeping track of that sum is keeping track of the number of successes. So it's the same as the number of successes in our sample divided by n. Right? Okay. So by the central limit theorem, we have that y bar is roughly normal with mean mu and variance sigma squared divided by n, right? And this is provided that n is big. Okay. Anyway, so what we can do is note that we could standardize, right? If that's true, that implies that let's standardize, let's subtract the mean and divide by the standard deviation of y bar, and then what we have is a normal 0, 1, right? So what we know is that then we could have something like this, that we could have negative z of alpha divided by 2 z, a normal 0, 1. We could have the positive version of this guy, and that probability should be 1 minus alpha. So then we could plug in and then solving for mu, we would have y bar minus that y bar, oops, plus, and then we would be multiplying by sigma divided by the square root of n, okay, so we will have basically the same thing here, but with a plus instead of a minus. Right, and here in the middle we just have mu, right? Now, going back to what we said here, if y bar could be thought of as the number of successes in our sample divided by n, well, that happens to be the same as p hat, the sample proportion. Sample proportion, p hat, right? And mu is p, and sigma square is p times 1 minus p. So what we have here is we could rewrite that expression in terms of p hat and p. This would be p hat, right? Sigma would be the square root of p times 1 minus p. That would be the square root of n, no problem. That's the same. Mu, instead of being mu, will be p, our parameter of interest. And then this guy would be the same thing, but with a p, right? So, last but not least, because that's important, we are going to be using p hats here instead of p's, right? Because we have to be able to find that from information coming from our sample. We don't know p. That's why we're trying to come up with a confidence interval for it. Make sense? So, bottom line, the formula for a confidence interval for a proportion is given by this: p hat plus minus c star times square root of p hat times 1 minus p hat divided by the square root of n. Okay, this guy is our new formula, and as you can see, we are relying on the central limit theorem, so we need a decent sample size. Okay, and in our slides we mention one way of checking if the sample size is big enough for the central limit theorem to work well. Okay, so what you will have to check is that n times p hat and n times 1 minus p hat is greater or equal to 10, and then you have the reassurance that the central limit theorem will work well. Okay, so let's go back to our lecture notes, and now we know where that formula came from. Okay, so it's basically just an application of the central limit theorem, right? And we just relied on what we did before for y bar, right? But for those 0, 1 random variables, those Bernoulli random variables, okay? Okay, so now these make sense. N must be large. We are relying on the central limit theorem. We are assuming independence, and that the random variables, the yi's, right, are Bernoulli random variables. They're independent. They have the same distribution, meaning they have the same p, the same probability of success. Okay, so now let's do an application of this. An example. Got it? Did you take a look at it? Okay, so as you can see, well, in this case, our parameter of interest is a proportion. It's the proportion of employees who typically take work with them on vacation. That's the proportion we would like to estimate. Okay, so we want to find a 90% confidence interval. Okay, and here part B is just an intermediate step. We're going to find the margin of error first, and then at the end we provide the confidence interval for that proportion that we are interested in. So part A, let's solve that problem. Part A. So first, what we want is a point estimate for that proportion. We know that it's going to be number of successes in our sample divided by sample size. So p hat in this case is just going to be 158 divided by 473. Make sense? Okay. So p hat is our point estimate, and is going to be number of successes, which is 158 divided by 473. Okay, so let's do that using R. (158) divided by 473, so roughly 33%. Okay, let me round it to 4 decimal places. Okay, so that's our point estimate. Part B. Let's find the margin of error. The margin of error, right? The margin of error is just, C star times the standard error, or C of alpha divided by 2 in this case, if you want to use that fancy notation. C of alpha divided by 2 times it's going to be the square root of p hat, right, times 1 minus p hat well, let me do it with symbols first, and then we'll do it with numbers. P hat times 1 minus p hat. Oops. And I want square root of the whole thing, right? Okay, that's better, but let me change that one Okay. Divided by the square root of n. Okay. So, in this case, since we want a 90% confidence interval, one way of finding it would be using R, if you have access to it. Then, since alpha is 10%, alpha divided by 2 is 5%, so we want qnorm of 0.05, and remember that the default is a normal with mean 0 and standard deviation 1, so it would be negative 1.64 something. Let's round it to 4 decimal places. This would be our guy, right? So that would be just this. Note that we had the negative version. If you want the positive version, you know that what you want is 1 minus that, right? Make sense? Okay. So then times, and we are going to be doing this with numbers now, right? It's going to be the square root of 0.334 times 1 minus 0.334 divided by n. In our case, n is 473. Okay? Okay, so let's find the margin of error using R. So it would be 1.6449 times, and then we have 0.334, right? 0.334 times 1 minus 0.334, right? But we need the square root of the whole thing, right? So it would be square root of this divided, and this is the square root as well, right? We need the square root of 473. Okay, okay. So let me go back to this. So it would be the square root of this divided by 473. Agreed? Because, you know, we could have the square root for both of them at the same time. Right? Makes sense? So the margin of error would be this. And again, we could round that to 4 decimal places. Let's use that. And finally, our confidence interval. It's going to be point estimate plus minus margin of error, right? So point estimate plus minus margin of error what we have is this guy plus minus this guy, right? And that's it. So the lower confidence limit is that, with a minus, and the upper confidence limit is that with a plus. Make sense? Right? Okay, so let me show you what we have here in our lecture notes. So basically what we have, right? Now this is going to be slightly different, because if we use our table we have to settle for 1.64 or 1.65, and that's exactly what I did here. I used our table. Remember, you can find it in page 848 if I remember correctly. I believe I'm right. Anyway, so then the margin of error is slightly different, right? But as you can see, you end up with basically the same result. Okay? Makes sense? And this is what we had here. Okay? Okay. So, now, finally, let me show you how we can do this very quickly using R. It turns out that there's a built-in function in R that is going to allow you to immediately, automatically find a confidence interval for a proportion. Okay? So, the syntax of that function that you are going to be using, which is prop.test, is first you need the number of successes in your sample, then you need the sample size, then the desired confidence level, in this case 90%, and finally, since we want R to give you the same answer that you would get using our formula, our calculations by hand, we're going to set correction, continuity correction, equal to false. Okay, so let's give it a shot. If everything goes well, we just have to copy and paste, and we'll get it right away. So from 0.2993 to 0.3705, that's your 90% confidence interval. We compare to what we had by hand here, and really close, right? Again, remember that here on our lecture notes I used a different critical value, the one that you would get using our table, so that's why we have a small difference, but really close. Okay, make sense? Okay, so let's summarize what we did here in this video together, you and I. So the problem that we wanted to solve right now was introducing the concept of a confidence interval for a proportion, right? And the formula is going to be p hat, where p hat represents the sample proportion, plus minus a margin of error. The margin of error is c star times the square root of p hat times 1 minus p hat divided by n, right? And what we said during the derivation of these formula of this formula of these two ends, right? The lower confidence limit and the upper confidence limit. With what we said when we derived those limits for our confidence interval is that basically what we're doing there is relying on the central limit theorem, right? So that's why you need a decent sample size, right? So you have to check that n is big enough for the central limit theorem approximation to apply, okay? And what you're going to be doing there, one way, an easy way of checking is doing this: n times p hat and n times 1 minus p hat must be greater than 10. Okay? Okay. Well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.